My name is Matthew Hall, and this is my lab report for the lab regarding constant velocity. Now, the idea of constant velocity results from Newton's second law, and he states that the net force of an object equals the object's mass times the net acceleration. And the net acceleration and the net force being directly related to each other. Therefore, if a force is introduced into the system, then in theory, the ball or the object will accelerate. The purpose of this experiment is to graphically and mathematically model a relationship between the changes in an object's position as a result of a constant change in time. This is going to be modeled in both a computer model and a physical model. The physical model being a ball rolling down, and then the computer being through GlowScript. Now, one of the additional concepts that's used in this experiment is Newton's second law as it relates to the momentum principle. What the momentum principle tells us is that the final velocity of an object is equal to its initial velocity plus an effect of a net force. So net force divided by mass times a change in time. And the net force divided by mass equaling the net acceleration of an object. Now, what we know for this experiment is that it must be at a constant velocity. This means that there is zero net force that is applied to this system according to its specific time constraints. This means that if the net force equals zero, then time, as well as the net force, has zero effect on the velocity change, which means that final velocity equals initial velocity. It is also important to note that the momentum principle can be applied to a change of position. The final position of an object equals its initial position plus a velocity times a change in time. This means that both the change in time and velocity affect the movement of an object, the displacement of it from one place to another. A time must elapse for it to change positions and a velocity, as we'll see, for our soccer ball to move from one place to another. Now, part of the procedure is I took a soccer ball and I rolled it across a parking deck, and through meticulously chosen points of 0.476 meters and 0.316 meters for an elapsed time of 0.1 seconds, I yielded an approximate velocity of 1.5 meters per second. Now, the reason why this is an approximate velocity is because there are many factors that come into a physical model in a realistic world, such as forces of friction, which will deviate our experimental velocity from a theoretical velocity. And in this instance, my data changed by about 5% from the information that I gathered from GlowScript. This is the coding information, and as you can see, our net force, as similar to our experiment, is 0 in all coordinates of a vector. And this is important because it replicates our idea of a constant velocity. Additionally, as you can see, it yields a linear line and you'll see in the data, with a very similar velocity. This is important because this singles out why coding is good for simulations, and it helps us to predict what can be in the future for any hypothetical movement problems. This is the comparison between the observed and computational model, and according to the graph, you can see that the computational model yields a slightly higher velocity than the observed model. This can be proven because of the force of friction. When you roll a ball, conceptually you have both a translational movement and a rotational movement. The rotational movement being strictly induced by the force of friction, which creates a torque on the ball. The translational movement is the relationship of the ball according to the earth, and it moves in a straight pattern. As you can see through the tracker, it's strictly horizontal movement. Now, all of this together combined creates a force of friction that yields a slightly smaller velocity. However, regardless of this discrepancy between the two velocities, it's still rather similar, which means that the constant velocity was proven to be relatively accurate. Additionally, we know that there was a net acceleration involved, rather subtle, but it was involved nonetheless. Because of the fact that the object was stationary, the soccer ball was stationary before I induced a net force into it. Even though the ball rolled at a constant velocity, we know that it began with an acceleration. And gradually, through the force of friction, it decelerated into a slightly smaller velocity that would not have happened if it was strictly a simulated process. In conclusion, we find that although the ball was rolled and observed through a tracking system, it yielded a very similar velocity to a more simulated environment. Now, to answer a few questions, if you flip the axes in this graph, nothing changes except it becomes inverted. Now we would have time on the y-axis and distance on the x-axis. We would get a seconds per meter. However, the shape of the graph wouldn't change. It would remain linear, but the numbers, the velocity would be flipped. Additionally, if we can't, what does this say about individual forces? Well, because of the fact that this is both simulated and an inaccurate representation of how an acceleration or a force affects a ball in a system, it is hard to single out net forces specifically. What we can do is we can identify every change in time. We can create an acceleration due to the changes in velocity. However, that doesn't tell us what our net forces are. It is very difficult to isolate how both friction affects it and how the acceleration from the previous force of pushing the ball affects